Okay, so let us consider this as another example for cantilever method. So although the beam is a low-rise building, because of height is less than the width, it is specified on the problem that we're going to use cantilever method to solve for shear along BE, reaction at A, and moment at A. So first, this frame is no longer uh, symmetrical. So the first step is to locate the center of gravity of all of the columns. Okay, center of gravity. So to do that, we first have a reference line. Say I'll just draw a line here as our reference line. Okay. And then you assume another line for the centroid or the center of gravity. Okay. This is the center of gravity. And it is x bar from your reference line. So we have to take note, as we have mentioned on the previous lecture, that we're going to involve here the size or the section of the column. So when we say size or dimension, we refer to I. Okay, what is I? Centroidal moment of inertia. So each of the columns will have a moment of inertia in terms of the area. And then from that, we're going to have a transfer distance from the location of the center of gravity. On our previous problem, on the first problem on the cantilever method, it so happened that your structure is symmetrical, but this time it is already unsymmetrical because we have a different base span here. This is 6 and that is 8, meaning the centroid will have an eccentric effect to the column because of the symmetry or unsymmetrical or the imbalance on the dimension. Okay, so first things first, we are going to solve for x bar. So that is the very first step, and again involving I in this particular problem. I is not specified, or the section is not specified. So what we do is to delegate. See, this is area 1, area 1. See, this line is area 2, and this is area 3. So we delegate those ones and assume it to be one unit. So 1 unit here represents that these columns are of the same sizes. Okay, that these columns are of the same sizes since it was not specified on the problem. Okay, so we are now ready to determine our x bar. Now the concept is similar in getting centroid. So we sum up A times x. So the total area is 3. So 1 plus 1 plus 1, that is 3. And then the distance of area 1 from your reference line is 0. because area 1 coincides from your reference line, and then we add area 2. The distance from your reference line of area 2 is 6. Then we have to add the last segment, and the distance is 14 from your reference line. So we assume all of this to be equal to 1. Then this is already 0. So x bar here is equal to 6.67 meters. So if this is 6, this shall be equal to 6.67 meters. And we take note that this distance is 0.67, and we just deduct that from 8 to solve for this distance. We have 7.33 meters. Okay, so that is the first step. Okay, and then for the next step, so regardless of the unknowns here, I'll just show you the whole procedure. Okay, again, we consider here point of inflections for the beam. First, we are going to consider the upper portion. Okay, so I'll just have to copy this string. And then just delete the lower portion because we're going to consider first the upper portion. So for the upper portion, again, we highlight the location of the center of gravity. Okay, and then what will be the rotation? It is actually rotating, clockwise if we tend to apply 25. Say this is M1. I'll just delegate that as M1. And what will be the value of M1? We just have to take note of the distance here. So 3 is bisected. This is 1.5. So therefore, M1 is simply equal to 25 by 1.5. So M1 is 37.5 kilonewton meter. And then from that, we're going to label the directions of the axial forces. Because we are on cantilever method, the first thing to solve is the axial forces. So it must be against the direction of this. So your boundary is this red line or the center of gravity. So we rotate this one a clockwise moment. So therefore, let us have an oppositely directed rotation to counter this M1. Okay, so this must be going downwards. So this is PCB. And this is PDE. PCB, PDE. And what would be the direction of this? So it is on the right of this center of gravity. So if we tend to rotate that one, so your counter flow direction would be going up. This is PIH. So let us also indicate our shear. VCB, VDE, and VIH. Okay, so we now get the values of those axial loading. So the general formula is P M C all over I. So I here would be transferred to the centroid. Okay, so how is I computed? Again, we refer to the location of the centroid. So it's simply I is equal to summation of area times the distance from the center of gravity. So therefore, I, first we have this one, area 1, times D1 plus area 2 times D2 plus area 3, D3. So area 1 is 1. By the way, this is squared, because that is a transfer formula. So what is the distance of 1 from the center of gravity? That is 6.67 squared plus area 2, this one. So 1 times 0.67 squared, and the D, this one, or area 3, is also 1 times 7.33 squared. So I here will be equal to 9.67 meters raised to 4. So next we're going to have now the corresponding forces. So PCB, starting with PCB. What is the moment involved? M1. C, or the distance from the centroid, is 6.67 all over 98.67. And of course, we have this to be 37.5. So that PCB is equal to 2.53 kilonewton. So we do the same to DE. We have M1, that is the distance of DE from the centroid, that is 0.67 divided by 98.67. So PDE, we substitute again 37.5, and so we have 0.25 kilonewton. Next, let's copy this IH. This is IH. We just change this to how much? This is IH, that is 7.33. So we have 2.79 kilonewtons. Okay, so before we proceed to the next unknown, I think we should complete all of the uh, actual loads here. So we have already considered the upper portion, so this time we consider the lower portion. So we're gonna delete this. Therefore this is 2 meters. So we highlight again the location of the centroid. So it will have a rotation like this. Same, going to delegate that as M2. Then from M2, okay, this shall be, both are going down, this is going up. We have PAB, PFE, and then we have PGH. So we solve for M2. So M2 shall be equal to 25 times 5. Okay, stick moments at this point. 25 times 5, and then plus 50 times 2 is equal to 225 kilonewton meter. Okay, then from this we can compute for PAB. So we have MC over I, M2, C over I, 225. So the distance from the centroid is 6.67. So we're going to use the same I, 98.67. So for PFE, we have 225 times 0.67 all over 98.67. So finally, we have PGH is 225 times 7.33 all over 98.67. So these are just the distances of this volume from the centroid. So we can compute now. And so we have the following values. Okay, so let's complete this one. This is VAB, VFE, and this must be VGH. Okay, so we have obtained all of the actual forces. Now we proceed to the unknowns. So for shear at BE, So for shear at BE, we're going to use the portal on B. See, this is portal on B. See, this is B. On that, we have here 50. And we have already obtained this, which is actually PAB 15.21. And then also we have here upwards PBC. VBC. See, this is the unknown VBE and EBE. So we still need to proceed on the upper portion. On the upper portion, because there are too many unknowns here, let us see if we could reduce the unknown out of this portal. So this is 25. I think we have already obtained this. PCB. Where's PCB? PCB is a downward force and was computed to be 2.53. Downward force and 2.53. So this is 2.53. Therefore, this must be also equal to 2.53. And we have here shear. So I'll just follow this direction. The opposite of this, VBC. And then this is PCB. Okay, so what can we get from that? If we're going to take moments at this point, observe that we can get the value of BC. So this point is point C. So we take moments on this one. We have negative VBC. This is 1.5 and this is 3. So we deduct this one, negative 2.53 times 3 is equal to 0. So VBC shall be equal to 2.53 times 3. 7.59, or this is negative. So we place it in here. So that we can now take summation forces vertical here. We have going upwards 2.53 minus going downwards 15.21 plus upwards VBE is equal to 0. So 15.21 minus 2.53 is 12.68. So we have 12.68 kilonewton for the shear at BE. Next, RE. So we further go down for RE. So for RE, we need to have this one. Say this is VAB. Okay. So what can we get from that? Now we are going to take moments at this point. Say this is 0.2. By the way, this is 0.1. So we take moments on 2. We have right clockwise 2.53. Okay, so we need to have this distances. This is 1.5. This is 3. How about we have 2 meters. So we take moments at 2. We have clockwise 2.53 times 3 minus this one, but we carry the sign, times its moment arm of 1.5, and then minus this one 15.21 times 3 plus VAB times 2 is equal to 0. So VAB is equal to by the way, we have forgot the moment arm of BC, 1.5. Perhaps we can revise this. So we have 5.06 kilonewton for VBC. This is negative. 5.06. This is 5.06. Hence we have 15.23 kilonewtons. So if we know VAB, we can already determine the moment at A. So this is VAB. So all we need is the distance, 2 meters. Of course, there is also here 15.21, and this is 15.23. So MA is equal to 15.23 times 2. We have 30.46 kilonewton meter. So this is MA. Okay. So next unknown, reaction at A. Okay, so we have already have here our AX and RAY. So this is RAX. Then RA is equal to square root of RAX squared plus RAY squared. And obviously, you just have to get these two values here. 15.21 squared plus 15.23 squared. So therefore, RA is equal to 21.52 kilonewton. So okay, so that's it for this problem. We have already solved for the three unknowns: shear at BE, RA, and moment at E. So for practice, I think you should have to resolve this and solve for all of the forces. Okay, so that will be a good practice for you. So thank you, and see you on the next video lecture.